Welcome everybody. Last time I think we were discussing that infinite series which was the result of the compound interest problem. And there are a lot of aspects of that series. You can call it Euler series if you want. I would like to discuss whether it converges, diverges, what is monotonically increasing, monotonically decreasing, what is alternating, not alternating. There are many aspects of those series, that series we need to discuss. But before we do that, there are a bit of background knowledge that you need to get in the other aspects of mathematics like algebraic geometry, even geometry itself, then trigonometry. We have not even covered the beginning of it. So I would like to cover those aspects first before we go back to our infinite series and see what exciting things that we can see. So now I'll start with one age-old problem that the Greeks had when they started doing measurements, geometry. One of the problems was finding the area of a triangle, of course. All of us know area of a triangle. We know the formula. We take one side of the triangle and call it the base and measure the height of the triangle as a vertical distance from the other vertex to the base. That is the height. And half multiplied by base multiplied by height is the area. Everybody knows this. We can measure those two quantities and multiply. That is actually there is one multiplication and one division, really speaking, in terms of computation wise. We are not very much worried about the computations today because every one of the devices that we use, like a computer or even a handheld mobile or a calculator, can do computation so fast. We are not thinking of those things. But early days, remember in old Greece, they did not even have a positional number system. They were using Roman numerals. Their addition itself was an effort. For example, please add LIX to XV or something. Some stupid addition like that. That itself is going to be an effort doing that computation. So obviously they are worried about the number of computations also to do that. First thing. Secondly, on the measurement itself, when you say I want to measure the base, you can measure the base. It's the horizontal distance. Remember this. When you say height, height is not height actually. Height is a perpendicular direction measurement on the ground only. We are talking of measurement on the ground. Many times what happens, if I want to find the area of a big triangle, for example, which surrounds this building, just take this building itself as an example. Now the side you can measure. On the side, one side you can walk across and take the measurement, but you have a problem with the height because the height goes through the building. There is no way you can measure the height. It's not possible, no? So then, so they had this issue there that you can measure all the three sides. That is not a problem. But measuring the height is going to be an issue. So how do you find the area? So this problem was addressed by one Greek mathematician named Heron. We should remember his name because he invented this formula at a time when actually algebra as a subject, as we know it, didn't exist. Symbolism didn't exist. The way we represent sides of a triangle as ABC or vertices and angles didn't exist. He invented this formula at that time. However, we'd like to prove it with our current knowledge of whatever arithmetic that we know, using only Pythagoras theorem. So we would like to do that first, as the first exercise today. Okay. So now what we have is we have a triangle. And I am not actually interested in even giving a name for the vertices. We have measured the three sides. That has been done already and we intend to find the area. So we can, if you had the vertices as ABC, you will get the sides, opposite sides. We call them by the names A, B and C lowercase. This is the standard notation. You will see the importance of this naming in terms of one topic which I already hinted about, talked about, called symmetry. Symmetry is extremely important from the point of view of memorization and also not making a mistake when you start doing some derivations. So to get the symmetry, you have to have symmetrical way of writing things, and this is one good way of doing that. So now I dropped a perpendicular. Now ABC are known values. We know those values, we have measured them. Now we dropped a perpendicular on paper. I called it H. H is an unknown. We don't know it. We have to calculate the value of H actually. Once you calculate the value of H, area is very simple. Area will be half AH. Now when you drop the perpendicular, I get a point on the base on which, that is the base, that is the foot of the altitude. And so now that gives us, that splits the side A into two pieces. I'd like to give a name to know. For that distance, we'll call this D. One piece I will call it D. The other piece I will not give another name because we know the value now. Once you know this D, if you know this D, then the other piece will be A minus D. Correct? So now I've got these A, B, C, H, D, the 5 quantities here, out of which we know 3 quantities already. The other 2 we need to compute, H and D. Now if we apply Pythagoras theorem, we got 2 right angle triangles here. If we apply it on the 2 right angle triangles, we'll get 2 equations which contain, both will contain H and D, as you can see that. So the approach, let me write down the approach to our solution first, before we actually go and solve it, is A. First thing is, we know 3 quantities A, B, C are known already, and D and H are unknown. Second, we have 2 right angle triangles of that shape that I have shown, and we apply Pythagoras theorem. So which means we get 2 equations which contain both these unknowns. Then we can try to solve or eliminate one of those. So next step is eliminate H. From the 2 equations. Once we do that, we can substitute that value of H back into one of those equations and calculate the value of D. Or if you eliminate H, which means compute the value of D. We find the value of D. When you eliminate H, you will get a value of D because all the others are known in that equation. And once you have value of the D, substitute D in one of the equations and compute H. This will be the approach that we want to use. Okay? So we'll start with that. So what is the first Pythagorean equation? So the square on 2 sides is sum of square on 2 sides is equal to square on the hypotenuse. So is D squared plus H squared equal to C squared. This is the first equation. Now we have one more right angle triangle and one more Pythagoras equation you will get is H squared plus A minus D whole squared equal to B squared. How do you eliminate H from these 2 equations? Just do a subtraction. You have got H square there, H square here, just do a subtract. Very simple operation there. So you will get D squared minus A minus D whole square will be equal to C squared minus B squared. Correct? And we can expand this. This is D squared minus A minus D whole square is A squared minus 2AD plus D squared. So minus A squared plus 2AD minus D squared. Correct? Which means minus A squared plus 2AD is equal to C squared minus B squared. So what is D? c squared minus b squared plus a squared divided by 2a. Correct. So now we substitute this value of d into this second equation. And we can find the value of correct value of h. Let's do that. I don't know whether it's going to work out, but let's see. So, what is the second equation now? Is h squared plus a minus d whole square is c square minus b square. Is that correct?
No, not c square, b square.
Equal to b square. So h squared itself is equal to we take a 2a common factor here. I think we can do that. Correct?
H square plus.
H square plus. So what is h squared equal to? B squared minus a squared minus c squared plus b squared divided by, you can write 4 squared by 4a squared. Now there are, if you calculate as it is, you will have to do one multiplication for each square, 1 plus 1 plus 1 plus 1 plus 1. 5 multiplications, another square, 6 multiplications, followed by 1 division. Correct? No? That is the number of calculations I am saying. We need to reduce that. We need to simplify this. How do we do that? Okay. Now let me take the LCM 4a squared. This is 4a square b square. I can write that as 2ab whole square minus a squared minus c squared plus b squared whole square. Correct? Now this form a squared minus b squared. Now x squared minus y squared. We know what we can reduce that as a plus b multiplied by a minus b. See, that is the reason it was written like that. So this will be 1 over 4a squared multiplied by a plus b multiplied by a minus b will be 2ab plus a squared minus c squared plus b squared multiplied by 2ab minus a squared plus c squared minus b squared. Correct? Now inside you can see I got on a square plus b square minus 2a plus 2ab. So we can combine that into a plus b whole square minus c square. Correct? Similarly, here I have c squared minus a squared plus b squared minus 2ab, which is a minus b whole square. Again, I have got this a squared minus b squared inside, no? Two pairs. So we'll split that again, we'll combine that as two factors, no? 1 over 4a squared multiplied by a plus b plus c multiplied by a plus b minus c. That is this factor. Other one is c plus a minus b multiplied by c minus a plus b. Correct? It has worked out quite nicely. Now the thing is to read this also. You see, now I am looking at symmetry. You have to think of symmetry. A plus b plus c is symmetric. A is there, b is there, c is there, no problem. Now I got on a plus b minus c, then c plus a minus b, and c minus a plus b. All combinations definitely I will not be able to memorize. No? So how do we write that combination correctly is the next question. Plus, can we reduce the number of computations that we need to do? Also is a question. Let us see how we can do that. Now first, this is the value of h squared. So h will be square root of this. When you take square root, I will get a 1 over 2a here and the square root of all the rest of it, right? So now area, we can write the area itself. The area will be equal to half ah, correct? Will be equal to, that a will get cancelled with, I got a 1 over 2a here for h, right? So when you multiply by 1 over 2a, I will get 1 over 4. A will get cancelled. Square root of, rest of it is in the square root, correct? Now these four expressions, you have to write them nicely for symmetry. A plus b plus c, you can write it as it is, no questions, it is symmetric. Now the other three fellows, if you see, they have one minus sign. One fellow has a minus c, another fellow has a minus b, third fellow has a minus a, correct now? So how do we make it symmetric? I can do one thing. I can even rattle off symmetrically saying a plus b minus c multiplied by b plus c minus a multiplied by c plus a minus b. Also is possible. But there is another way of looking at it. We'll write that same, since anyway I have computed the value of a plus b plus c. I have to calculate in any case. So I will write the rest of it as a plus b plus c minus 2a. Will be actually a plus b minus a, sorry, b plus c minus a. That is the last expression. Multiplied by a plus b plus c minus 2b multiplied by a plus b plus c minus 2c. Correct? Now, easier to remember now. Now, how do we simplify it further? We can have a notation or even introduce a new variable for a plus b plus c, because that is common for all the four factors. We can compute that first, so I can call it something. And that I'll get something minus 2a multiplied by something minus 2b is again not a very good way of thing. If that were to be some 2 something, no, then I could take a common factor of 2. So we substitute now a plus b plus c. So we substitute, this is a trick, equal to twice new variable. 2s. Normally, it is called 2s. Now, what is s? Half of a plus b plus c. And what is a plus b plus c? Is the perimeter of the triangle. That is the addition of all the lengths is the perimeter. So, s is actually known as the half perimeter. when we make the substitution, I'll get a plus b plus c, which is 2s, multiplied by 2s minus 2a, multiplied by 2s minus 2b, multiplied by 2s minus 2c. We take the 3 2s as common factors outside. There is a fourth 2 here. So all the 4 will come out of the square root as 4 only. They will even cancel that other 4. So I will be left with square root of s multiplied by s minus a multiplied by s minus b multiplied by s minus c. And this is a formula I learned about 54 years ago. I have not still forgotten. What is the area of a triangle? Square root of s into s minus a into s minus b into s minus c. How will you forget that formula? No? Impossible to forget. That is the kind of symmetry that people need to achieve. You understand? And now the number of computations also, if you see, for computing s, originally to start with, what has he done? He has done 2 additions, correct? He added b and c to a. So it is 2 additions, I'll write as 2 plus. Then I've got 3 subtractions I have got to do here. So 3 minus. I need to do 3 multiplications, 3 stars, and I need to do 1 square root. So totally, now you can see 8 additions and subtractions and 1 square root will find the area of the triangle. That is the absolute minimal number of computations that you need to do for doing this. Even for computer algorithm, this is the best way of calculating, is to represent the area as square root of s into s minus a into s minus b into s minus c. I have only one issue with this, this formula for the area of the triangle. How did Heron derive this? 2000 years ago. That is the only question. I have not been able to answer that question. Okay.
Before algebra, how you respond?
Okay. On the sake of symmetry, there is something else I need to discuss for the triangle, some more symmetric issues, but unfortunately that requires some other background. So we'll start with that background. Okay. As part of this, I'd like to pay homage to one of the great French mathematicians of 14th century, whose name unfortunately we don't hear anywhere. That means nobody is paying any respect to our gentleman, and I think he deserves appropriate respect. So his name is Nicole Orisme. In the 14th century, he did a lot of pioneering work in mathematics, and one of the things he is still remembered is for proving divergence of harmonic series that I'll show you next. But he did many other works there which served as background for other French mathematicians. And one of the famous French mathematicians of that time was René Descartes. In the French language, they write all kinds of apostrophe, comma, dash, and hats, and and pronunciation is always a problem. No, we call it. I call it René Descartes. It is actually Descartes, but it should be called Descartes. No, one problem. If you look at another name, for example, French mathematician, if you do an Indian pronunciation, is Cauchy, but actually it should be pronounced Cauchy. Cauchy is the pronunciation. Anyway, it doesn't matter. I think these translators also had the same problem with the name. No, like they had a problem with Al-Khwarizmi's name. When they Latinized that name, they called him Algorithmi or something, right? So That's why we got the name algorithm. And these people also published, unlike Newton published his Mathematica Principia in Latin only, whereas these French people are saying, no, I don't write Latin, I will publish in French only. So he published his works in French only, and that had to be, unfortunately, translated to Latin so that the other European people or mathematicians and scientists could read. And when they translated René Descartes' French treatise, first thing about the name itself. So what is the Latinized name of René Descartes? Is Renatius Cartesius. This is the name, Renatius Cartesius. That's why Descartes' coordinate system, we call it Cartesian coordinate. Why Cartesian? Because his Latin name was Cartesius. That is one issue. So he came up with this coordinate system, the background of which, like I said, had already been worked by Orisme. He had already worked it out, but then he didn't quite present it in the way it looks like now. The first aspect of that is, we've already seen that representation of the plane. When you have the plane, for geometry we start with a plane, plane and a point on a plane, line on a plane and so on. So the first aspect is, when you say I've got a line on the plane, I can have any line on the plane, but I would like to have something called a reference line, which maybe points towards east. As I said, is one popular way of writing it. And of course, the other part of the same line, if you extend it, will point to the west. Now, any point on this line, on the plane, can be used to represent a number, real number. So, assuming that one point on that line is assumed as a 0. 0 is the additive identity. So, assumed as 0. So, as the number, real number, positive numbers are positive distances towards the east, and negative numbers are negative distances towards the west. So that's how we represent that. That means, if you look at the real numbers, I mean, what is a real number also is a question. And if you think real numbers, I've got a set of real numbers. That means all real numbers are there, put together as a set. Set means not, I don't know, whether you put them in a mound or whatever. Just imagine that I put all the real numbers in one group or one set. You can call it a group or a set. Now, there is always a one-to-one matching, unique matching between the real numbers and the line. That's why this line itself is called the real line or the real axis. Every point on the real axis represents a real number. Every real number has a corresponding point on the real axis. Positive numbers will be on the right side of 0. Negative numbers will be on the left side of 0. And this line can keep going all the way towards infinity. Infinity is not really a number. And backwards it goes towards minus infinity. Again, minus infinity is not a number. Infinity is just an indefinitely large number. That means it is larger than any large number that you can think of, is infinity. So, same way, minus infinity is less than any small number that you can think of. Now, the natural numbers, that is our 1, 2 and 3, these form, you can think of them as another set of numbers which we call natural, because they are natural. Natural numbers, they are called natural numbers because they were originally used for counting, 1, 2, 3, 4. They are counting the objects or items or cows or buffaloes or sheep or whatever. So they are the natural numbers, and each natural number has got a point on the axis at that distances. That is a unit distance. That distance is fixed. And now these natural numbers were not sufficient. We need to be able to have partial numbers also. So we had the next set of numbers. So we rationalized that. Actually, they are not natural. Natural numbers are natural only. But these fractions, if you take p by q, for example, where p and q are two natural numbers, they are not actually natural. You can't use them for counting purpose. But we rationalize, saying yes, we want to have them also as part of our number system. So we get what are called rational numbers. So we got a set of rational numbers, infinite number of them, which can always be represented, any of them can be represented as a fraction of two natural numbers, positive or negative. So as a ratio of two numbers or two rational numbers we want, that also is there. And these rational numbers, there are infinite number of the rational numbers are there, which means between any two natural numbers or any two rational numbers, you would find an infinite number of other rational numbers. Again, between any two of those infinite numbers, you will find infinite number of, you understand, you think that this axis is very dense with numbers, no? It is very dense, you will think it is what we call dense. How many points are there? It is very dense. Rational numbers are dense in that sense, but actually they are not called dense because there are gaps in rational numbers also. So there are some numbers which are not even rational. No? That means they cannot be expressed as ratio of P by Q. For example, simplest case is square root 2 or something. Square root 2 is an example. That means the solution for an equation like x squared is equal to 2. Simple equation, quadratic equation. What is that solution? Cannot be represented as a fraction of two integers. So it is not rational by any sense. So what do you call it? In that case, if it is something is not rational, we will call it irrational. We call it irrational. What else? There is no choice, right? So we call it irrational. So irrational numbers will also include solutions of any polynomial equation. Any polynomial. Quadratic equation, cubic equation, any degree. To any degree you take, those polynomials have roots and their roots can be rational or need not be rational, then they are irrational. So now we combine the irrational number set also as part of our number system. And remember, every irrational number has got a corresponding point on the real axis. No questions on that. Now you would think that irrational numbers, once you add them to rational numbers, now it really becomes dense, what we call dense. Now there is no gap in the real line. Every point on the real line is either a natural number or a rational number or an irrational number. No questions on that. So now irrational numbers also, people found there are types of there actually it falls into two categories. That is, the definition of irrational number is a number which cannot be represented as a ratio, as a rational number. But then there are two types of it. One is roots of polynomials is one group. But there are some irrational numbers which are not even roots of polynomial numbers. They are called transcendental numbers. I mean, there is something, what is transcendental? Whatever it means, when they just called it transcendental, no? So something to do some superhuman type of numbers because they are not even solutions of polynomial equations. Those are also there and they are also part of the, now we'll call all of them as real numbers because what is a real number now? Definition is very simple. Real number is a number which can be represented as a point on the real axis. That is a real number. So obviously, if you say I've got a point somewhere here outside the real axis, is not a, what is it? It's not a real number, no? It's not a real number, correct? So any point outside the real axis cannot be, I don't know what it represents. Definitely it does not represent a real number. And something when it is not real, what do you call it? Imaginary. So that discussion of imaginary numbers we'll discuss at a later stage, but this is not the time for it. So we'll still stick to real number system only. Then how do we represent points on the plane? Remember, what we are trying to do is, once we convert a point on this real axis, point on this line into a number, we can start working at it with algebra. No? We can start doing algebraic calculations on it instead of just doing geometry. So I am trying to do geometry in an easy way as a series of calculations, just like Heron did for that area of triangle. But many of the other calculations I would like to do using numbers or variables. How do we do that? Is to be able to represent geometrical objects using numbers. Now, on the real axis, no problem. So one line, all the points we have represented, but what about other points on the other lines? So what you need to do for that is to visualize a second real axis, really speaking, perpendicular to the first one. This is the Descartes contribution through the same 0 point, what we call origin. We draw a perpendicular line and say, now this is another real axis which also has got a positive direction towards north and a negative direction towards south, correct? So that means I can take any point on this other real line that also represents a real number, and once you have these 2 points, I can represent any point on the plane by simply dropping a perpendicular to the two lines that I have drawn, 2 real lines. In fact, in this case we call it real x-axis, horizontal axis, and this we call it y-axis as a standard notation. So any point if you take is at a distance from the y-axis, that is actually that distance is in the x direction. So it's got a distance on the x direction, which is a real number, and a distance in the y direction, which is another number. So a pair of numbers can always represent any point in the entire plane. This plane actually is known as Euclidean plane because Euclidean geometry works on the plane. Now we can call it Cartesian plane, Descartes plane. So it is known as Cartesian plane because any point here can be represented as a pair of real numbers. Normally we write that on paper in brackets saying something, something, comma, something, something, close bracket. So we write 2 numbers inside brackets which is separated by a comma, 2 real numbers, and that can represent a point. For example, I can have a point which is 0, 0. What is 0, 0? Is the origin. 0 distance along the x-axis and 0 distance along the y-axis. So that is a origin. The natural numbers, any natural number n, for example, is n comma 0 because it is a 0 on the y-axis. You understand? We can do that. Or in general, you say I got a point, we need 2 values to represent it. You can call it x comma y. That means x is the distance along the x-axis and y is the distance along the y-axis. So x comma y will represent any point in the plane. And if you have 2 points to be represented, call them x1, y1 and x2, y2. You have 3 points, what do you call them? By symmetry. Call them x1, y1, x2, y2, x3, y3. So if you have a triangle on the plane, how do you represent a triangle? As 3 pairs of coordinates, x1, y1, x2, y2, x3, y3 should define any triangle on the Euclidean plane. Now, how we do that? How we use that as part of geometry is known as analytical geometry. Okay, so we look at that, how we can do some geometry using algebra. That is the topic. How do we use Thales theorem? How do you use Pythagoras theorem? How do you find the distance between 2 points? How do you find the sides of a triangle? How do you use Pythagoras theorem? All these things we can discuss using algebra. So first thing is, when you say I've got a point are 2 points. Take any 2 points which are x1, y1 and x2, y2. First thing is you need to calculate distance between these 2 points. That means if they are the two vertices of a triangle, that will give you the side of the triangle. Now, what is the distance? Becomes the question, right? How do you find the distance? That we need to use Pythagoras theorem for it, like I'll show you. Just drop two perpendiculars to the axis through these points so that you get a right angle triangle. Now I got the two sides of the right angle triangle and the side as the actual side as the hypotenuse. And what is that distance? That is the distance between x1, y1 and x2, y2 should be square root of hypotenuse squared is the square of this plus square of this, right? So, and I need to take square root of it. And what is this distance? Is the distance of point 2 from origin x2 minus distance of point 1 from origin, which is x1. So, square root of x2 minus x1 whole square plus square root of y2 minus y1 whole square. Correct? Now, on the real line, there are two important properties I should have really mentioned, which I'll do that. I'll mention in passing, so to speak. I should have done that in the previous diagram. They have two very important properties. Real numbers or the real set. They're represented as capital R. They have two properties. One is closure. They are closed. That means any two real numbers, whatever operations you do on that, the result also will be a real number. When you say whether you add or subtract, closure on operations like addition, subtraction, multiplication. You add division also, except that division by 0 is prohibited. Other than division by 0, even division is included. So when you have two real numbers and do any of these operations, the result will also be a real number only. So the entire set is closed with respect to these operations. That is one property. The next property is it is ordered. Ordered really means when you have two real numbers, for example A and B, either A is greater than B, or A is less than B, or A is equal to B. There are only three possibilities. That is known as ordering. And ordering is transitive also. That means if A is greater than B and B is greater than C, if both are true, then A must be greater than C. Now that follows immediately from the geometric representation, because when you have 2 points A and B, either A is to the left of B or to the right of B or in the same place as B. You understand? And if A greater than B, A is right of B, B greater than C means C is right of B. Therefore, C must be right of A also. So that these two properties are very important for real number system. Not all sets have these kind of properties, closure and ordering. That is fine. Now, distance between 2 points that we have seen, no problem. Now, many times we need to find a point in between also. Supposing I want to find the center point. Like if I am drawing a median, for example, I need to find the midpoint of a side, correct? So how do you find the center point? In fact, by symmetry, if you want, I can write down the coordinates of the center point will be x1 plus x2 by 2, comma, y1 plus y2 by 2. This will be the center point between these 2 points. I have written it by symmetry, but we want to prove it also. But in addition, many times it's not just the center point. I want to find any point between these 2 points. That means this point is dividing this side into 2 parts. I am saying if they are equal, then it is a midpoint. They may not be equal, they may be in some ratio, correct? So I would like to consider that ratio and find out, given a ratio, how do you find that point? Is what I would like to do next? How do we do that? That means I have assume that, let me draw a bigger picture so it becomes clearer. Remember, these lines can be drawn in any direction, backwards, forwards, positive coordinates, negative coordinates, x and y are called coordinates, no? Because real numbers have got a positive and negative sign, the sign will automatically take care of those aspects. I am not really discussing in detail. Now, supposing I got a point here which divides this side in some ratio 1:n, whatever value of n. Correct? That means I've cut this distance into n+1 pieces, one piece on this side and n pieces on the other side. So what are the coordinates of this point is the question. For this, very simple is to drop the perpendiculars as usual. Drop the perpendiculars. When you drop perpendiculars, I got two parallel lines here and an intersecting couple of lines. Obviously, I get similar triangles. And when you get similar triangles, you can apply Thales theorem. You got the corresponding angles which are equal, right? So I can apply Thales theorem. So how do you apply Thales theorem? Let's give some names to these points. Let me call this A, B are the two original points. Point in between, I will call it P. I got drop the two perpendiculars. You can call them D and E. So I got the two triangles APD and ABE are similar. Triangle APD similar to triangle APE, ABE. I have to write the vertices in the correct order so that the matching angles are written in the correct same position, right? Angle A, angle P is the same as B, angle D is same as E, which is correct. And once you do this, Thales theorem can be applied. Therefore, AP by AD will be equal to AB by AE. First two letters. AP by AB is equal to AD by AE. That's the correct way of writing it. I always write this by exchanging the numerator and denominator, doesn't matter. You could also write it as AP by AD is equal to AB by AE also, doesn't matter. So now our interest is in finding out the coordinates of P, right? So AP is what we have to find actually. Coordinates of P, which is actually AD. AD gives you the coordinate of P, right? So I need to calculate a value of AD. First we exchange these two, so we bring n into the equation. This implies AP by AD equals AB by AE. And AP I already have the AP by AB, no? So I don't need to do this exchange also. What is AP by AB? 1 by n plus 1. 1 and that is n, right? So 1 by n plus 1 is that ratio. So AD is equal to AD by AE is equal to 1 by n plus 1. Therefore, AD is 1 by n plus 1 multiplied by AE. Correct? And what is AE? Is the x coordinate of B minus x coordinate of A. Similarly, in the y side also same thing will happen when I draw up a perpendicular. So what I suggest is that we will work with only with the x coordinate abscissa. By symmetry you can write down the answer for the ordinate, which is the y coordinate also. So what is AE is x2 minus x1. By n plus 1. That is AD. So therefore, what is the coordinate of P? That is, we are trying to find xy. What is x? Is x coordinate of A plus AD, which is x1 plus x1 plus x2 minus x1 but divided by n plus 1. Correct? Take the LCM n plus 1. So this is n plus 1 x1 minus x1. So I will get n x1 plus x2 divided by n plus 1. N x1 plus x2, that x2 is actually 1 x2, really speaking, divided by n plus 1. So which means, when you say I am traveling from, just imagine, you are traveling from A towards B on this line, correct? The more you travel, you will have more dependence on the point B, no? Less you travel, you will have less dependence on the point B. That means, actually the involvement of the x1 is in terms of the distance not travelled, not yet travelled. That's why you multiply that n by n, nx1. For B is the distance which is already travelled. Now, influence of B is the distance we have already travelled towards B. Influence of A is the distance yet to travel from A. So that is why nx1 plus x2 by n plus 1 will be the x coordinate of P, and by symmetry we can write down what is y, n y1 plus y2 divided by n plus 1. Correct? No question. But if you want to find out, prove it, just drop the perpendiculars to the y-axis and apply Thales theorem, you will get this expression, n1 plus y2 divided by n plus 1. Okay? Now, this symmetry, my topic now is symmetry only. I don't want to, now you say I can find the area of a triangle using the 3 coordinates, I can do many things. I can find the altitude, I can find orthogonal bisector line, possible, using coordinate geometry or analytic geometry. But that's not my interest. My interest with this topic was to show you the importance of symmetry, correct? So for that, I will take one of the geometry theorems which we did earlier and try to prove it through analytic geometry and show you how simple that proof is. Okay? Okay. Now, what we want to do next is to prove the theorem that medians of a triangle are concurrent. That is the proof that we want to do, right? So we draw a triangle as usual. In fact, in analytic geometry, you don't even need to draw the triangle. No, we need the coordinates of the vertices, right? And if you look at one median, A, B, C, let's assume these are the vertices, has got a center point. I will call it D. I should have really called A as the top vertex, the standard notation. I just shown the median. I'm not actually drawing a solid line for it. So what we need to do now is the other medians, the other two medians. We got two other medians, one from B and one from C. Even if we take one of those medians, that is going to intersect this median at one point, no? So I am interested in a point on AD, actually speaking. And how do I reach the point? First, I have to go from B to D. Towards C, I have to go half distance because I know that is a bisector. D is a bisector of BC now. And from D, I need to travel up towards A. This is what I do, correct? On the two lines. And I reach that point. You can call this point, what do you want to call it? G. So I write the coordinates now. So I got A, B, C, x1, y1, x2, y2, x3, y3 are the three coordinates. Therefore, what is point D? Is from x2, y2, I have to go towards x3, y3, but halfway, correct? So therefore, this will be x2 plus x3 divided by 2, comma, by symmetry y2 plus y3 divided by 2. That is the ordinate. In fact, since symmetry is going to work both ways, we will not even bother writing the y coordinate for the moment. We can write that in the conclusion only. So I am only looking at x coordinate of this. X coordinate of D will be x2 plus x3 by 2. And from this we want to go towards A. We don't know where this median is going to intersect. No? Another median is going to intersect at some point, which need not be the center of AD. It could be any ratio in which it cuts that line AD. So let us assume that wherever it cuts, I will mark the ratio as 1 and n. I still don't know what is this 1 and what is n, right? So that means I from the point D, I want to go towards a distance of 1 by n plus 1. That is it. So how do you write the coordinate, x coordinate of G now? Is the next. What is it? Is the x coordinate of D multiplied by the distance not yet travelled. So that means x2 plus x3 by 2 multiplied by n plus x coordinate of A, which is x1 multiplied by distance already travelled is 1. Correct now? It's the same what I wrote earlier.
x2 plus x1. G is x2 plus x1.
It's correct. Divided by n plus 1. This is correct. x2 plus x3 by 2 is the x coordinate of D. We multiply by the ratio not yet travelled, n, plus x1 is the x coordinate of A, multiply by the distance already travelled, which is 1 actually, divided by total distance to be travelled is n plus 1. The same, correct now? Now, the question is very simple. This is the x coordinate of G. Everybody knows that. Now, I want to make that symmetric. Now, how do I make that symmetric? Is there a value of n that I can select such that this value becomes symmetric? No? So, how do you do that? I got x1 here with no coefficient. Now, coefficient is 1, whereas x2 and x3 have got the coefficients n by 2, right? So, how do you make all the three coefficients the same? What is the value of n that you select? Select n equal to 2. If you select n equal to 2, what will you get as the G's coordinates now? x1 plus x2 plus x3 divided by 3. Correct now? Perfectly symmetric. So if you use the same ratio for the y coordinate, what will you get? y1 plus y2 plus y3 divided by 3. No questions on that, right? Now, this is the point, correct? So now if I join B to G, for example, Or I won't even join it. How did we get this coordinate actually? We traveled from the midpoint of one side and traveled towards the third vertex 1/3 of the way. Correct, no? Now, it so happens I have selected BC as the example, that is x2, x3, and then traveled towards x1, no? In fact, if I had selected, instead of this, supposing I had selected A and B as the side, from x1, x2 midpoint, travel towards x3, 1/3 of the way. What would I get? I would get the same thing, symmetry. Or I can select AC as the side, x1, x3 midpoint, and travel towards x2 1/3 of the way. What would I get? Same x1 plus x2 by symmetry, x1 plus x2 plus x3, which means now you can see the median from B must go through G. There is no choice. And it will be 1/3 of the way from center of AC. Similarly, the median from the center of AB must go through G, same point. Because that is the same, that point is common now, it is for all the three medians. Therefore, medians are concurrent. I have not even drawn a single median. Without drawing a single median, you can prove all the three medians are concurrent. No construction, no median. Just a simple algebraic proof because of symmetry. Correct? Is that clear? It will be no problem. Now, I want to talk of some other symmetry aspects. But before we do that, we need to introduce concepts of trigonometry. Now, I have to take up trigonometry. We are not even started on trigonometry. I'd like to start on that. Okay. So, we'll start with some definitions of trigonometry. As you know, sin x, cos x, jya and cottage jya, original names given by Aryabhatta. So, if you say I've got a right angle triangle, in fact, what I want to do is not start with the triangle, would like to start with the original thought process of Aryabhatta, where he did the so-called parikramana. Going around in circle, no? Parikramana we do in temples, no? So, starting point, there is a center and there is a starting point, and we go one round, full round. When we do that, because we are now thinking of Cartesian coordinates, now you can see this starting point itself can be treated as the original real line or x-axis, that is to the east. And to the north, of course, will be the moment of one right angle or 90 degrees or pi by 2 as you call it. And to the east, to the west is a 180 degree movement, and to the south will be 270 degrees movement, right? So this is the movement that we are talking of. And when we do that, what happens is that the person who is walking on the circle, if you look at the center, he is and the two axes, we got the x-axis and y-axis basically. The two axes, east is x-axis, north is y-axis. He is moving towards the center on the x-axis when he starts moving, and he is moving away from the center on the y-axis as he starts moving. No? So that means at any point, we've already moved some distance on the y-axis, and we have moved towards the center on the x-axis. What is the distance is the question. Now, I could have drawn a circle of a smaller radius and distances would be correspondingly smaller, but by Thales' theorem, we know the ratio of that distances to the radius is constant, right? So we can assume, in fact, we can assume that it is a unit circle. That means 1 is the radius. That 1 can be 1 meter or 1 kilometer or whatever, 1 dozen meters, You can think of some unit as a 1 now, that itself. In fact, I think Aryabhatta used some 22,400 and something as that base unit of radius now. So easy for calculations. It doesn't matter what number you use because we are only talking of ratios, right? So now the distance in the vertical direction that we already traveled is half of that card is the jya, are known as the sine. Sinus or sine, and the balance distance to the origin on the x-axis is known as the cosine or cos or cosinus. Cotijya or cosinus or cosine or cos. So this is the value of that angle that we have moved. So this is the angle now. So this angle, again, angle measurement we can measure in terms of degrees. So degrees is, so I got an angle here, and what is the name of the angle that we use? In the case of triangle, if you recall, we use the letters A, B, C themselves for angles. Names of the vertices used for angles. Now here we don't have a triangle, we are not discussing geometry here. We got some angle anywhere, anywhere on the plane, from anywhere to anywhere. So these angles, we don't use these uppercase alphabets. We use, popularly earlier they are trying to use Greek alphabets, alpha, beta and gamma for the angles. But then writing these, I don't know, I don't like to write alpha, beta and gamma and so on. It becomes difficult. The only Greek letters that have become totally familiar are a few. Like for example, pi is one. Everybody I think has to become familiar with pi. There is no choice. Ratio of the circumference to diameter of any circle, right? So that is fixed. Then epsilon as the lowercase e, in the Greek alphabet, name suggests any small positive number. We call it epsilon, indefinitely small, and also delta, both. That is lowercase delta, d. Lowercase d is delta. So epsilon and delta are used to represent infinitesimal quantities or small quantities, not infinitesimal, small quantities. The infinitesimal quantities, we use the delta sign, uppercase delta. That is, if you write, for example, delta x will be an infinitesimal change in x. What is infinitesimal change? Is not just very small, it is infinitesimally small. So, that is delta x. Whereas epsilon and delta are small numbers. So, in fact, this part of the infinitesimal calculations or calculus we will need to be discussing. Now, if you have an angle there, what is the letter which is popularly used is a theta. Theta is what is used. We can use theta, no problem. Very popular, cos theta, sin theta. Or you can use x itself as an angle, lowercase x. So you can have cos x and sin x if you want, or you can use cos theta, sin theta. Or sometimes if you use geometry to prove some trigonometrical theorem, for example, we go back and start using a and b itself. We say sin a, cos b and so on. So even that is possible. So you should become familiar with all of these different nomenclatures. So in this case, I'll just call it theta. So we have one sin theta, which is the vertical distance which is travelled, and cos theta, cosine theta or cos theta, let me just write that as cos theta only. Is the horizontal distance from the still from the center. Now as we start moving, now you can see on the real axis sin theta is 0. We are not yet travelled upwards at all. It starts with 0. So theta is 0, sin theta will be 0, and cos theta will be 1 because we are not yet travelling. We are not yet started travelling towards the center. So sin 0 is 0, cos 0 is 1. When we hit this vertical axis, we have completed the vertical travel. So sin theta will become 1 actually. Sin 90 is 1, cos 90 becomes 0 because we have reached that center there. And when we continue further, sin theta will start reducing from 1 all the way back to 0, and cos theta will start reducing from 0 towards minus 1. Actually, it starts becoming negative. Now, cos theta becomes negative here. So, here sin theta, cos theta both are positive in this part of the Euclidean Cartesian plane, and this part is known as actually the quadrant 1. So, we got 4 quadrants. Quadrant 1, quadrant 2, quadrant 3 and quadrant 4. In quadrant 1, both sin theta and cos theta are positive. Quadrant 2, sin theta is positive, cos theta is negative. Quadrant 3, cos theta is still negative, sin theta starts becoming negative. Both are negative. Quadrant 4, sin theta is still negative, cos theta has become positive. So, that is one other thing that, in any case, sin theta and cos theta are oscillating between minus 1 and plus 1. In both cases, they never go out of that range. They're always between minus 1 and 1. In fact, that range itself on the real line, supposing you have 2 points A and B on the real line, we define what is known as an interval. Okay, interval. All the points on the real axis between these 2 points A and B, that is known as an interval. Interval, we write it in different forms. One is open bracket A comma B, close bracket. This is known as a open interval. Open interval. What is the meaning of open? Open means ends are open. So, this open interval does not include the endpoints. That is the meaning of open interval. A and B are actually not in this open interval. Other than A and B, everything else in between is the open interval A comma B. Then we write square bracket A comma B close square bracket. This is the closed interval. Closed interval includes the endpoints A and B also, and all points in between. That is known as closed interval. Now you can have partially open. That is open on one side, closed on the other side, or open on the other side and closed on this side. So we can write them as open bracket A comma B close square bracket. So it is closed on the right side. It includes B but does not include A. Or I can write open square bracket A comma B close ordinary bracket. This is closed on the left side but not on the right side. So we use these to say I want to have a number in this interval, for example. I want to have a number called x in this interval. So we write that as x belongs to this interval, A comma B. So this epsilon, slightly written bigger, is belongs to, that is the nomenclature. X is a real number in this open interval. Now, that's how we write that. X belongs to that. So this is one more notation that we have to get familiar with. There are two more Greek, not Greek, I don't even know whether it's a Greek or not, two more symbols that you have to get used to. One is this. Is a vertical capital A, no? Write that. This means for any so I can write that before this x. I can write that. For any x which is inside the open interval A comma B, if you want to write it, you write it like that. And there is one more symbol which is capital E written backwards. I don't know where that letter has come from. This means there exists the meaning of there exists, whatever, depending on that theorem that you are trying to write in algebra, you use these symbols. For any, there exists belongs to epsilon and delta In fact, many times they call it epsilon delta technology. The two small numbers, they were invented by some famous mathematician. Newton, for example, used this without even his knowledge. But then later on it was rigorously formalized, and that epsilon delta technique of specifying a theorem, that was actually discovered by a mathematician and used by him thoroughly, and everybody now accepts that that is one of the best ways of describing limits and derivatives and anti-derivatives and so on, epsilon delta method of describing it. So we'll see that. That's a different issue. So now, like I said, sin theta and cos theta are always in that range. In fact, I can write that one statement. For example, I've gone one full round, so angle has become 2 pi radians or 360 degrees. We don't want to use degrees in calculation of algebra, we prefer to use radians. So we have reached 2 pi. I can continue again. No? One more circle I can continue. Angle can become more than 2 pi also, right? But sin theta will still be the same -1 +1 range, right? So which means for any x which is a real number which is in the interval -infinity comma +infinity open interval, because I am not including, actually there is no -infinity +infinity, they are not numbers, remember. So any real number, x is any real number for any x belonging to a real number, right? I should have written x belongs to that range, right? One of the points in that range. There exists, if you want, a cos x, and what is the range of cos x? Will be between -1 and +1, right? So how do you show that? I can find the modulus of that absolute value and say that will be less than or equal to 0, less than or equal to 1. Is one way of writing that statement if you are interested. I am saying you will find in mathematical papers and theorems, you will find these notations, and all of you should become familiar with them as soon as possible. So I thought this was a starting point to write one statement. I may not use this statement, just as an example, I have given that particular statement, right? So that means there is no limit on this angle. What I am saying is angle can go from -infinity to +infinity. So, and if you start in the opposite direction, it will start going negative. So there is a negative angle actually. Below this is a negative, positive that side. So once you have this cos theta and sin theta, now it's time to start using them as part of our trigonometry itself, as part of our geometry. What is the first thing? Is to find the area of a circle, right? Area of a triangle. Back to the same question. Supposing I've got a triangle and I want to find the area. How do you do that? So I got 3 sides. If you want, I'll write the names for the vertices A, B, C. May not even be necessary. And I'll drop the perpendicular. If you want to find the trigonometric functions of sin theta, cos theta for any of these angles, you need 90 degree. You need right angles, no? Without right angle, you can't. So what is the definition of sin theta itself? I'll call this foot of the perpendicular as D. Sin means sine of an angle, obviously. Sine of an angle, what is the definition? If you look at this, sine of an angle is the opposite side, opposite to the angle, no? Opposite side divided by hypotenuse. Sine is always in a right angle triangle, of course. angle is one of the non-right angles of a right angle triangle. Sine of an angle is opposite side divided by hypotenuse. Similarly, what is a cosine of an angle? Will be adjacent side divided by hypotenuse. Right? And many times as part of our algebraic workouts, we'll need to cross multiply them. That means what is opposite side? I just take this hypotenuse to the other side. So what is opposite side equal to hypotenuse? Sounds very simple. Multiplied by sine. And what is adjacent side? Is hypotenuse multiplied by cosine of the angle, of course. They are always true. I can make use of these. Like for example, if you wanted to find out what is AD value is, just imagine in this right angle triangle ABD, I get an angle B, right? And this is the opposite side of angle B. So what is the value of AD? AD is hypotenuse multiplied by sine of the angle B. Correct, no? That's how we work it out. Let's just write that down. No? Sounds very simple, but it can lead to a dramatic amount of symmetry. That's why I want to write it down. So what is AD? Hypotenuse multiplied by sine of angle B. Correct, no? Now, the sides also, I don't want to use this AB, BC, CA and so on, so we'll give the other names. That is, our lowercase a is the opposite of vertex A, B opposite of vertex B, and lowercase c opposite of vertex ABC. So, what is this AB sin B? C sin B. So, what is AD is C sin B from this right angle triangle ABD. I have taken right angle triangle ABD. In fact, I have got one more right angle triangle. So, this was right angle triangle ABD gave me this answer. I got one more right angle triangle which is ADC. Also has got the AD, no? So, what is AD here? Hypotenuse multiplied by sine of the angle, no? Right? What is hypotenuse here? Is B sine C. B sine C. Therefore, both are same. So, what is B sine C? C sine B. So, now we write the symmetric equations for it. How many such equations you will write? 3 such equations. So, what is A sin B is B sin A. What is B sin C is C sin B. And what is C sin A is A sin C. Correct, no? So, now, easy to by heart, you will never forget in your life. Now, A sin B is going to be sin A. Very simple to remember. And if you want to simplify this even further, we can transpose some of these, provided they are not zero, of course. Now, in an actual triangle, remember, the angles are never zero. No? A is not zero, B is not zero, C is not zero. So, sin A is not zero, cos A is not zero. So, obviously, sines and cosines are non-zero. So, you can always take them to the other side. No? So, take sin A this side, sin B that side. What will you get? A by sin A equal to B by sin B. And that will be equal to, obviously must be equal to C by sin C. By symmetry I can write it. It's here, actually it is here. A by sin A is here also, which is C by sin C. So now this is even more easier to remember than the previous three equations. Now I got only one equation. A by sin A is equal to B by sin B is equal to C by sin C. That means when you have three angles of a triangle ABC, the three sides ABC are in the same ratio as sines of those angles. Sin A, sin B, sin C. Sin A, sin B, sin C ratio is there. Same ratio is there for ABC also. That is the meaning of A by sin A is equal to B by sin B is equal to C by sin C. So this is the first symmetric theorem in geometry, trigonometry, right? Next is the area of a circle. We can write now, we can go to the area. What is the area of a circle? I can calculate in n number of ways. In this case, I will use BC as the base and AD as the height. If we do that, will be half multiplied by base, which is A, multiplied by altitude AD, and AD we already C sin B or B sin C also. You can write both. Also, I can write B sin C. Half AB sin C. That's the area. By symmetry, I can also write would be the same as half BC sin A will also be the same as half CA sin B. All three will be the same. All three will give you area. In fact, so this gives you one more equation to remember. AB sin C is equal to BC sin A is equal to CA sin B. Big deal. Okay, it's the same as A by sin A equal to B by sin B equal to C by sin C. So area I can find if you have two sides and the included angle. Actually what you have is AB are two sides, included angle is C, and what is the area? Half AB sin C. Correct, no? Now, and we also knew that if you knew the three sides also, all the three sides ABC if you knew, we know the area as square root of Heron's formula is there. S multiplied by S minus A, S minus B, S minus C. So that means if I know the three sides, I can use this formula to compute area. If I know two sides and included angle, I can use this half AB sin C formula to compute the area. Then what is the other case, is I know one side and two angles also is quite possible. How do you find the area? Right? I know B and C and the side A. Also decide the area, right? How do we do that? I know side A, I don't know B and C, but I know the angles B and C. What is the area? Just write it. That is, we know the value. I want to find the area. Given area, I should not write as A equal to, I should write as area equal to, right? Area. Is actually half AB sin C, but unfortunately, I don't know the value of B, but I know the value of capital B, which is the angle B, no? Right? So how do you find the value of B? Use this formula. B is A sin B by sin A. Half multiplied by AB multiplied by, sin C I want. Sin C will be C sin A divided by A. But then I will get C there. I don't want C. I want A only. Yeah? I want to find the value of B using only A and sin A. So I must use this first formula only. So B will be A sin B by sin A. So it will be half a squared what is 1 over sin A? We have one more trigonometric function what we call cosecant. Cosecant A sin B. Okay. I have not defined this cosecant. 1 over sin is called cosecant, 1 over cos is called secant, sin over cos is called tangent, 1 over tan is called, cos over sin is called cotangent. So 6 trigonometric functions, but anyway, I want to look at this in a bit of more detail, not in this particular format, for which it requires a separate discussion. We will do that shortly. Okay.